So a stochastic matrix is any square matrix with non-negative entries. And columns sum to 1. So that's how stochastic matrix is defined. Okay. Yeah, that's right. It's a transpose of the one that we are using. One thing that you can easily verify is that, uh, for example, if I have a vector which is 1, 1, 1, 1, this is a right eigenvector. With eigenvalue 1. So you have this matrix P, you can compute its usual right eigenvector, and corresponding to eigenvalue 1, the right eigenvector is very simple, all the entries will be 1. Of course, typically it will be normalized such that sum of all the entries will be 1 for the eigenvector. And the corresponding left eigenvector is the one that gives you the invariant probability distribution. So you shouldn't confuse between these two eigenvectors. These two are two different things. And so if you have a right eigenvector which is like this and corresponds to eigenvalue 1, this already means that there is an eigenvalue 1 and corresponding left eigenvector. And what you need to show is that this corresponding left eigenvector has all non-negative entries. Okay. So which means that let me put in two conditions. Let me call condition 1 that left eigenvector can be chosen to have all negative entries. And second condition is that condition number 2, that the eigenvalue 1 which is guaranteed to exist is simple in the sense that it does not have multiplicity. Okay. So eigenvalue 1 is simple and all other eigenvalues are less than 1. Okay. So every other eigenvalue is smaller than 1 in modulus. Now the point is that if you can satisfy these two conditions, then whatever the result that we got for the two-state system will hold in general for a general case as well. So you see actually in our two-state system and also in the three-state case, if you remember, the two-state case follows both these conditions in the sense that the matrix P is non-negative. There's no zero at all in the matrix entry. It's all some positive number. Whereas in the three-state case, P has some zeros. Okay? So that gives rise to a problem that we will soon come across. Okay, so one thing that you can easily notice is that if I have the transition probability matrix whose elements are like this P1, P2 up to P1n and maybe Pn1, Pn2 all the way up to Pnn. And since it sums to 1 across a row, and this is always true. This is trivially true in such a case, which itself is a very hand-waving proof that eigenvalue 1 exists for such a case. Okay. And you also have a right eigenvector which is simply populated by 1, 1, 1. You can normalize it and so on. And this also tells you that a left eigenvector with eigenvalue 1 also exists. Okay. So now the question is what kind of eigenvectors or what kind of matrices will satisfy these two conditions. And there is one large class of matrices which satisfy both these conditions, and that is guaranteed by what is called the Perron-Frobenius theorem. This is the centerpiece of this Markov chains. Important result. So if I have a stochastic matrix P, such that all entries are strictly positive, which means that there should be no zeros in your stochastic matrix. So that is Pij is greater than 0 for all Ij. Okay. Then this Perron-Frobenius theorem tells us the following. Asserts that 1 is a simple eigenvalue of P. That means that a unique eigenvalue with unique eigenvalue 1 exists. Second is that the left eigenvalue can be chosen to have, left eigenvector can be chosen to have all positive entries. And hence it can be since it can be chosen to have all positive entries, it can be a probability vector. So a probability vector would be something like this. So if I have a vector like this, P1, P2 and so on up to Pn, if all these numbers are positive, then you could, and of course all this sum to 1, then you would call it a probability vector. And the third condition is that, the third thing that it says is that all other eigenvalues are strictly less than 1. That is, lambda I is less than 1 for this one. So this last part, the fact that all other eigenvalues are less than 1 also implies that that your eigenvector is simply the stationary eigenvector, or any initial condition would actually converge to that. Okay, so I am not going to prove this theorem. You will find it in many textbooks. Neither is it something that can be done very quickly. So let's take some initial vector v0, which I can write it in terms of the eigenvectors of the eigenvectors of P. Okay. Now, if I have to evolve this V0, what I would do is P to the power this is what I would do, which is equivalent to saying that I would do something like this, but I know that P acting on Vi is lambda I Vi. So, if I use that here, this would be lambda I Vi, okay, summed over I. Now, since lambda 1 is the largest of the eigenvalue, you can actually take it out. Where is my? Yeah, lambda power n. Yeah, okay. Okay. To make it easier to follow what happens, let me take lambda, let me multiply and divide by lambda 1 to the power n, alpha I, lambda I by lambda 1 whole to the power n, Vi. Now what happens? So in the limit that n tending to infinity, this from this equation you can actually see that this one, the limit that n tends to infinity will actually simply go to alpha 1, alpha 0, alpha 1 V1. Which is simply your pi bar, which is proportional to your pi bar, the stationary probability distribution. And you can also infer a few things from this. See, V0 is your initial probability matrix. All the entries are positive there to begin with. Now, that was your initial condition that you had put in. And we know that P is, the way it was constructed is a transition probability matrix. All the entries are positive. So, follow through the arguments. You can then argue that pi bar also is a vector with all positive entries. Okay. Again, it's not a proof, but somewhat easier way of seeing the contention of Perron-Frobenius theorem. Okay, so now there are some, and another thing that you can also see is that given the fact that lambda 1 is the largest eigenvalue and every other eigenvalue is smaller than lambda 1, the speed of convergence to this pi bar is determined by lambda 2. Because the dominating is still lambda 1 is the dominant eigenvalue, and the speed with which your p power n v0 converges to pi bar will depend on lambda 2, the second eigenvalue. Simply because if you separate the that will remain lambda 1. The other terms will be, for example, in the summation, the next term will be lambda 2 by lambda 1. And if lambda 2 is much smaller than lambda 1 and you are raising it to power n, it's going to decrease very fast. So, how fast the other terms go to 0 matters. So, that is the speed with which you are converging to pi bar. Okay. So, in other words, I think lambda 1 and lambda 2 are two important quantities for this transition probability matrix simply because the first one corresponds to your stationary eigenvector and the second one is an indicator of how fast you can get to pi bar. Okay, looks nice as it is, but there are some issues. Okay. And to see the issues, we should go back to this example 2 that we had, that phone problem with 3 states. Okay, so I quite have it here. So you look at the matrix P that I have here, and this is strictly not positive definite. There are at least 2 zeros in that matrix. Okay, we cannot directly apply the Perron-Frobenius theorem, but let me try if it works. Okay. But now if you take P square, the square of this matrix, let me just write down the numbers. See, this is also a transition probability matrix, P square, but this has no zeros in it. But now you can apply Perron-Frobenius theorem to P square, not to P itself. Okay. So this satisfies the condition that Pij is greater than 0. Okay. So that you can apply this, and here one will be a simple eigenvalue of P square. And you will have an invariant probability distribution pi bar, and you will have second and every other eigenvalue which is smaller than 1. And interestingly, and it's a basic linear algebra property, that eigenvectors of P are also the eigenvectors of P bar. So now you can write down a general rule. Okay. If P is a stochastic matrix, such that for some n, P power n has all entries positive, then P satisfies that condition 1 and condition 2 that we had. Yeah, these. Yeah, these two conditions. Yeah. So now you can ask the question, under what condition can we conclude that P power n will satisfy these conditions? Under what conditions of stochastic matrix? So let's say you have a stochastic matrix with zeros in it. Okay. Under what conditions will it satisfy this? So for motivation, let's look at some examples once again. So a different example 1. Okay. This is an example we met before. Let's look at this. Random walk with reflecting boundary condition. on the state space of 0, 1, 2, 3 and 4. Let's do it in a simpler case so we can actually see what is happening. Okay. So now here I can write the probability transition matrix. Uh, okay. Now let's see, now if I actually take p power n here, again it's something that you can easily do that. I am going to get the following 0.25, 0, 0.5, 0. So this is what you will get if n is even. And let me take p raised to the power n where n is odd. In that case, I'll get something different. Let me, since I already calculated it. So again, not just n is even, but also n large. Okay, so this is when n is odd, and n of course is much greater than 1. Now you can actually see why there should be so many zeros in p power, and you can take n to any large number, you will always have these zeros, because in the random walk case, there would be, depending on the initial condition, certain probabilities would always be 0. Like for example, if you take, let's say something like this is your starting point, okay, let's say 1 and 2. Now you start from here. In one step you can come here, and in second step you can come here. So odd step you are here. There will never be a situation where on an even step you will be on an odd labeled site. It will never ever happen. So for all even times, probability of being in either 1, 3, 5, 7 is always 0. Okay. So it's simply a reflection of that. Do whatever you can, this is never going to happen. So this is then a sort of problem case. So a walker who is starting on a even site will remain on even sites, and a walker who is starting on odd sites will remain on odd sites. So in these cases, you will say that P has period 2. This transition probability matrix has period 2 because it is going to go between these two. At every odd time you will come back to this, even times you are going to come back to this. So in this situation, we will see that you will not be able to get a stationary vector. So let's look at one more example here. This is a random walk with absorbing boundary. So you've seen this before. Let me see if I can pull up that. Yeah. Oh, okay. I'll take P and Q to be half. So go back to that transition probability matrix. Put P and Q to be half, and you are going to get this. Okay, so this is P, and just to give you two, so this is 0, 1, 2, 3, and 4. This 4 and 0 are the absorbing states. Now, what happens here for large n? So, if I take Pn where n is very large, so this P power n, if I compute, I am going to get something like this. So, once again you see however large in n you take, you can't avoid zeros in this case. But here again physically you can see why it is happening. So, that is why I drew this picture here. So, all it says is that 0 and 4 are absorbing boundaries. You start the walker from anywhere in 1, 2 and 3, it does not matter. Eventually as time goes to infinity, it will go to either 0 or 4 and get stuck there. So, which is going to leave 1, 2 and 3 empty beyond a point, okay. And that is what is reflected in your P power n. So, as time goes to infinity, the walker will only be found in 0 or 4. So essentially the walker will settle down at 0 or 4, and hence this set of states 1, 2 and 3, these are called transient states. Triple zero half and half, yeah. No, the problem is that here you can't get a steady state distribution in the sense of Perron-Frobenius theorem, because it doesn't apply for whatever value of n. So there are, see, the whole point of these two examples is that even when you take p to the power n, there are examples where p power n will give you, like for example in the first case that we saw, p had zeros but p power n, 2 itself has no zero. So you straight away apply Perron-Frobenius. But the last two are examples where even when you take p power n, you still have zeros. Apply Perron-Frobenius theorem. But intuitively it seems like this. Yeah, that's right. Yeah, that you can't. It's not outcome of Perron-Frobenius theorem. Yeah. So these are two ways in which application of Perron-Frobenius theorem can fail. So if you have periodicity is one case, or you have something like an absorbing state, for example, that's one possibility. And one more, let me give you another example which is even more easier to figure out if you think about it. Let me just draw the Okay, it has a complicated structure. Okay, so and I can quickly write the P also. So here even from the figure itself you can figure out that 2 and 3 are somehow disconnected. So either it basically breaks into two small graphs. So there can be dynamics between 1 and 2, there can be dynamics within 3, 4, 5. And in fact that's reflected in your P matrix. It's actually it's a block diagonal matrix. So you have two blocks there. Okay. So it's a sort of disconnected this one. 4 to 5. 4 will be this, right? 4 to 5, that's 4. Oh, that's 5 by 24, yeah. 4 to 5 at the top, right? Yeah, okay. Now again in this case you can ask what happens in the large n limit. So you can calculate what happens in the large n. So once again I will not write all the entries, I have the numbers here, but it's important to just say that you will still maintain that block structure. So there will be zeros here, yeah, and there will be some non-zeros in the left and right. So in this case the chain splits into, the Markov chain splits into two parts. There is 1 and 2 and 3, 4 and 5. So within each chain it will converge to a invariant distribution, but as a whole it will not do. Okay. So this is an example of what is called a reducible Markov chain. So in other words, that you should not be able to split your set of states into two or many different set such that there is only dynamics among them. If you are able to do that, then it's a reducible Markov chain. So these are broadly like two different ways where your Perron-Frobenius theorem can fail. One is you should avoid periodicities, because if periodicity exists, then you are actually preventing it from reaching a stationary state. And if your chain splits into smaller blocks, that's another reason why things can fail, at least not satisfy the conditions of Perron-Frobenius. It's another recipe for failure, so it will not reach. So which means that let's now look at formally what is this thing called reducibility, or reducibility is easier to so it's indicated something like this. If I have two states, ij of two states ij that communicate with each other, Yeah, so maybe I should say. So, I mean, put in terms of probabilities, all it says is that you should be able to reach from I to j. The probability of starting from I and reaching j in m steps should be greater than 0, and probability of reaching from j to I in some other number of steps, n steps, should be greater than 0. If these two conditions are satisfied, then you say that these two states communicate with each other. So in other words, in a general graph setting, this is typically, this has to hold good for all possible states in your system. So if you think of a very complicated graph, this is possible if there is a, very colloquially saying, it basically means that I should be able to go from any point on the, in the graph to any other node in the graph. There has to be a path. If there is a path, time doesn't matter. Sooner or later you will reach there. So all the states which fall, which satisfy this, they make up a communication class. So like in the previous case, this 1 and 2 and 3, 4, 5 separately they satisfy this. So there are two communication classes in the previous problem. That's what you would say. And if your entire matrix P or your Markov chain has one communication class alone, then you would say that it's irreducible. Markov chain represented by P is irreducible if there is only one communication class. So this is the idea of irreducibility. So if you are able to communicate within a set of states, that is that they form a communication class. So in this example, there are two communication classes. And if there is only one communication class, then that's the whole P is called a irreducible. Yeah. M and N is any number of time steps. It doesn't matter. Yeah.
Then M and N can be same as well.
It can be same as well. Yeah. And the other question was about periodicity. So let's say that I have P, which is a stochastic matrix for irreducible Markov chain. Period of a state I is denoted by d of I, or simply d itself. Okay. This is simply is denoted to be the GCD, or the greatest common divisor of the following. Okay. So it means that the probability of starting from a state I and coming back to the same state in n steps should be greater than 0. So for a given state, you can list out what are the possible ends for which that can happen, and then take the greatest common divisor of those ends. I'll give you example. For example, in the first example that we did, the simpler phone problem, the period is actually 2 in that case. But let me give you a few simple examples of this. Let me draw some figures here. Let's say I just have 2 states like this. You can go from this state to this state, and you can go from here to here. Okay. So you can label it as 1 and 2. It doesn't matter, the probability of transition is immaterial. Okay. Now you can, let's say you start from the state labeled 1. To come back to 1, you will at least need 2. So you have to go and come back. You need 2 steps, but you can also come back in 4 steps, you can come back in 8 steps, and so on. So that means that the steps will go like 2, 4, 6, 8, and so on. And the GCD of this is 2. So the period of state 1, state labeled 1 is 2. Now you can do the same thing for period 2, but you don't have to do. If you get the feel for this, it's quite symmetric problem. So state 2 also has period 2. So in fact the entire Markov chain has period 2 in this case. But let's do a slightly different version of 2-state problem. Suppose I have this and this. So I have 2 states, and I go here and I add a self loop. So again, this is state 1, this is state 2. Okay. So now what are the ways of starting from 1 and coming back to 1? Okay, so you will have 3 and 4 and 5 and so on. So now you take the GCD of this is simply 1. Okay. So this is an irreducible graph by our definition. So this is periodic, the first one. So in other words, okay, let me maybe write it here itself. So if your period is 1, if you have period 1, then you would say that it's a aperiodic chain. So both are irreducible, which is true. Whereas this is a periodic chain and this is a aperiodic chain. Maybe let me give another one with 3 states. Yes. That's it. So I'm going to I'll just look at the period of state 1 here. If you look at okay, so what are the ways in which you can come back to 1? You can come back to 1 in 3 steps starting from 1, but you can come back in 6 steps, you can come back in 9 steps, and so on. So again, taking the GCD of this, it's simply 3. So that's the period there. And so one last example let me give you, like this. Like this. Like this. So once again, if you are looking at period of state 1 alone, you can see that you can come back in 2 steps. For example, if you take the lower root You can go from here to here and come back. So that would be 2 is one possibility, 3 is another possibility, then 4 is a possibility, and so on. 4, then 6, and so on. So you take a GCD of this is 1. So this is aperiodic. And typically, if P is irreducible and all the states within one class, one communication class that is there, will have the same period. In that case, you need not talk about the period of a state, but you can talk about the period of the entire Markov chain itself. Okay, so the key idea is that you need to be able to work with the Perron-Frobenius theorem, you need to avoid periodicity, you need irreducibility. So you need a irreducible chain and you need a periodic chain. Okay, so now this gives us clues to what needs to be done. So now you can refine your theorem, the Perron-Frobenius theorem. If P is the transition matrix or probability transition matrix, for an irreducible aperiodic Markov chain, then there exists a unique invariant probability vector pi bar that satisfies this. And further, if this is any initial probability vector, then so this simply converges to pi bar. So phi bar p power n goes to pi bar, and pi bar of I is greater than 0 for all I. That is, all the elements of the vector are greater than 0. So now we have ruled out all the cases where it will not work explicitly by adding the condition that your transition matrix or your Markov chain should be irreducible and aperiodic. So, okay, you may ask like, is it like complete disaster if you don't satisfy these two conditions? Not necessarily. If even if you had a reducible Markov chain, it just means that it doesn't work for the entire matrix, but for each communication class, this can still apply. It's not such a disaster, which implies that your result will depend on your initial condition, where you choose your initial condition. That is what it finally would boil down to. Okay. And if P is irreducible but is periodic, then essentially you will still have some probability, something, basically it would just depend on n, that's all. It would depend on time. The only problem is that you will still have some eigenvector which is not the invariant probability distribution, for that particular case. Or in some examples actually you can write the invariant, I mean you can factor in the n and write the invariant probability vector. So your invariant vector itself will depend on n. In fact, that is what happens in this kind of cases where you have this odd even problem. You can separately solve the problem for all the odd and the even cases, but you can even write one unifying vector by writing -1 to the power n and so on. So that way it will look like you solved it in general. So that's what it means. Okay, so before we go to the arbitrary graph case, let's just do two simple motivational examples to illustrate the Perron-Frobenius case. So this is a random walk on a ring. This is what would be called a random walk with periodic boundary conditions. So here is a ring, and I have okay, so I am going to assume that P and Q are half here. P is equal to Q is equal to half. That is probability for going left and right are both equal. And a few things you can easily see from here is that it's already an irreducible graph, and it is also aperiodic. These are simple things you can straight away observe. Now let's write the transition probability matrix for this graph. So it will be something like 0, half, 0, 0, half, half, 0, half, 0, 0, 0, half. Okay, so I have this one, and as I said, it is irreducible because you can go from any node to any node. Yeah.
Period 2.
Uh,
You have double edges, right? Anti-parallel edges.
yeah.
So any
No, this is not period 2.
Because there's an odd number of vertices, that's why this is.
This is because it has odd number of vertices. So if I had taken either 6 or something like that, you will have this.
one set of edges.
Yeah, exactly.
It's not a double-sided.
Yeah.
Or is it?
No, what is double-sided edge?
So in 1 and 2, you have 1 to 2 and 2 to 1 edges.
Yeah, both ways. Yeah, it is undirected.
So then I can come back to one in even number of steps, right? So because
Yeah.
I can go to one vertical outcome.
There's a 5 also, right?
There is also a phi. If you go around, you will come back in. Yeah. So in this case, it turns out that if you now take the limit of n tending to infinity of p power n, in fact, it's simply equal to 0.2 all over the place. So it's simply 1 by 5, 1 by 5, and so on. Okay. After seeing the result, of course, you might easily sort of think that physically that should have been, you should have thought about this, because I mean, purely from symmetry properties, every node is like any other node. There's no difference. Sitting on one node, the whole network will look similar in any node. So on an average, it should be 1 divided by the number of nodes, which is 1 by 5. Okay. So in the long time limit, if you launch a walker, on an average, the probabilities would be like this, 0.2 everywhere, which is 1 by 5. So here is a case where you satisfy all the conditions. Even though you have zeros in the original matrix P, P power n finally has no zeros. And here you can, for example, try things like let me, you can say I'll choose an initial condition, let's say this 5 bar, which is something like this 0.5, 0, 0.5, or any combination such that all the elements add to 1, and then you can multiply with this matrix, this one, and it will give you exactly 0.2, 0.2 everywhere. So here, for instance, if you do that, so let me call it P infinity. So this will give me 0.2, 0.2. And you can try simulations and check that this actually works. Now the last example is the other counter example that you just brought up. I am going to do the same random walk on a ring, but with n equal to 6. So it's the same ring, but I am going to put 6 nodes there. But here, so this is your this one. So clearly this is irreducible. Even by the looks of it, you don't need to do any analysis. But this is not aperiodic. Okay, so this is periodic. So here once again, if you write the P matrix, it will exactly look like the previous matrix that we have seen with halves in the two corners. You can just extend this by adding one more row, there is no difference. But yet, in spite of this similarity, the period is actually 2 in this case, because of the fact that period is 2. In this case, the condition that P power n should be greater than 0 is not satisfied. So this is not going to give you that invariant probability vector in the same sense in which you got the result for the same problem just with 5 nodes. So you can see what kind of difference it makes when you do a random walk on a 5 node ring and a 6 node ring. It illustrates the important point about this periodicity. So physically, if you think about it, you need to avoid periodicities. In some sense, periodicity in the chain would simply mean that you are not letting it thermalize. You are not letting the walker to thermalize into rest of the nodes that is available. It is simply getting trapped in some periodic cycles, and which is why your Perron-Frobenius won't work. Once again, you can, these are the kind of things you can do very simply, very easily using simulations and verify this. Okay, so tomorrow we'll start with generic arbitrary graphs. Till now, we have more or less been looking at one-dimensional cases, but it illustrated all the important lessons that we want. So there's nothing new in terms of content that we will see. Everything that we want to know is already there in the Perron-Frobenius theorem, but we'll apply that to an arbitrary graph and also see how you can use that to define centrality measures, the important one being the page rank. So we'll go through that calculation tomorrow. Okay.